Hello friends, welcome to this lecture. Myself Amlan. Today I will discuss about behavior of free electrons in a metal Fermi energy. Okay. Any piece of metal of macroscopic size contains a very large number of free electrons which are weakly interacting, identical and indistinguishable particles having spin half h cut. So, the free electrons in the piece of a metal are fermions, and so the assemble of free electrons obey Fermi-Dirac statistics. The number of free electrons in the energy interval epsilon and epsilon plus d epsilon is given by Fermi-Dirac statistics as dn equals to n epsilon d epsilon equals to g epsilon d epsilon by e to the power alpha into e to the power beta epsilon plus 1. Now let e to the power alpha equals to f. So this is equals to g epsilon d epsilon by f e to the power beta epsilon plus 1. Suppose this is equation 1. Okay. Now here beta equals to 1 by kt and g epsilon d epsilon is the density of states, and we know that for electron this is equals to 2 into 2 pi v into 2m by h square to the power 3 by 2 into epsilon to the power half d epsilon. Okay. Suppose this is equation 2. Since an electron has two independent direction of spin orientation, we multiply this expression of g epsilon d epsilon by 2, and v is the volume of the piece of metal and m is mass of each electron. Okay. Now under the condition f much greater than 1, that is e to the power alpha much greater than 1, we can neglect 1 in this expression, and so equation 1 can be written as dn equals to g epsilon d epsilon by f e to the power beta epsilon. Okay. Suppose this is equation 3, and this is identical with the corresponding expression for Maxwell-Boltzmann statistics. So under the condition f much greater than 1, that is e to the power alpha much greater than 1, the assemble of free electrons behaves as an ideal gas. Such behavior is called non-degenerate. So for non-degenerate electron gas, from equation 2 and 3 we get dn equals to 4 pi v into 1 by f into 2m by h square to the power 3 by 2 into epsilon to the power half e to the power minus beta epsilon d epsilon. Okay. So the total number of free electron is n equals to integration 0 to infinity dn equals to 4 pi v by f into 2m by h square to the power 3 by 2 into integration 0 to infinity e to the power minus beta epsilon to the power half d epsilon. Okay. Suppose this is equation 4. Okay. Now let beta epsilon equals to x. Let beta epsilon equals to x, or epsilon equals to x by beta. So d epsilon equals to dx by beta. So using this, equation 4 can be written as n equals to 4 pi v by f into 2m by h square to the power 3 by 2 into integration 0 to infinity e to the power minus x into x to the power half by beta to the power half into dx by beta. Okay. This is equals to 4 pi v by f into 2m by h square to the power 3 by 2 into 1 by beta to the power 3 by 2 integration 0 to infinity e to the power minus x to the power half dx. Okay. This can be written as 4 by v by f into 2m by h square to the power into beta to the power 3 by 2. Now if we calculate this integral, we will get root over pi by 2. Okay. Now if we put the value of beta equals to 1 by kt, then we will get this is equals to 2v by f into 2 pi mkt by h square to the power 3 by 2. So n is this. Hence f equals to 2 by n by v into 2 pi mkt by h square to the power 3 by 2. Okay. This is equals to 2 by, let capital N by V equals to small n. So this is equals to 2 by small n into 2 pi mkt by h square to the power 3 by 2. Okay. Suppose this is equation 5, where small n equals to capital N by V is the number of free electrons per unit volume. Okay. Now this equation shows that electron gas can be non-degenerate if n is small and t is high. Okay. Now if we put the value of m equals to 9.1 into 10 to the power minus 28 gram for electron, and suppose for copper n is of the order of 10 to the power 23, then we will find that f is much greater than 1 if t is of the order of 10 to the power 4 Kelvin, which is much greater than our room temperature, that is about 300 Kelvin. Okay. Now at ordinary room temperature, that is about 300 Kelvin, f is comparable to 1, and under this condition electron gas is degenerate. Okay. So we can say that at room temperature electron gas in metal is strongly degenerate. Okay. Now at low temperature F is much less than 1 for electron gas, and the quantity alpha is usually expressed in the form alpha equals to minus epsilon f by kt, where epsilon f is a positive quantity of the nature of energy. Okay. So we can write f equals to e to the power alpha equals to e to the power minus epsilon f by kt. Then we have dn equals to g epsilon d epsilon by e to the power epsilon minus epsilon f by kt plus 1. Okay. This can be written as f of epsilon g epsilon d epsilon, where f of epsilon equals to 1 by e to the power epsilon minus epsilon f by kt plus 1. Okay. The function f of epsilon is called Fermi function, and epsilon f is called Fermi energy. Okay. Now at t equals to 0 Kelvin, for epsilon less than epsilon f, the quantity e to the power epsilon minus epsilon f by kt can be written as e to the power minus epsilon f minus epsilon by kt. Okay. Now if we put the value of t equals to 0, then this becomes e to the power minus infinity, that is 0. And under this condition, f of epsilon equals to 1 by 0 plus 1 equals to 1. Okay. And for epsilon greater than epsilon f, the quantity e to the power epsilon minus epsilon f by kt equals to, if we put the value of t equals to 0, then this becomes e to the power infinity, that is infinity. And under this condition, the value of f of epsilon equals to 1 by infinity plus 1, that is 1 by infinity equals to 0. Okay. So we can write at t equals to 0 Kelvin, f of epsilon equals to 1 when epsilon less than epsilon f, and equals to 0 when epsilon greater than epsilon f. Okay. Thus, at absolute 0 temperature, f of epsilon is a step function. Okay. Now we want to draw energy epsilon versus Fermi function f of epsilon graph for temperature t equals to 0 Kelvin. Okay. If we plot energy epsilon along x-axis and Fermi function f of epsilon along y-axis, then at absolute 0 temperature we will get this type of graph. Okay. And this is Fermi energy, this corresponds to Fermi energy epsilon f. Okay. So this graph is for temperature t equals to 0 Kelvin. Okay. Thus at absolute 0 temperature, all the quantum states for energy below Fermi energy are occupied by the free electrons, and all the quantum states for energy above Fermi energy are unoccupied. Okay. Now at all non-zero temperature, that is t greater than 0 Kelvin, when epsilon equals to epsilon f, the value of f of epsilon equals to 1 by e to the power epsilon minus epsilon f by kt plus 1. Okay. So this is equals to, if we put epsilon equals to epsilon f, then this is equals to 1 by e to the power 0 plus 1, that is 1 by 1 plus 1 equals to half. Okay. Thus at temperature t greater than 0 Kelvin, that is at temperature above absolute 0, the value of f of epsilon is half. That is, at temperature t greater than 0, the probability of occupancy is half. That is, 50% of quantum states are occupied and 50% are empty. This gives the physical interpretation of Fermi energy at temperature t greater than 0 Kelvin, that is at a finite temperature. Okay. Now if we want to draw energy versus Fermi function graph for temperature t greater than 0 Kelvin, then we will get this type of graph. Okay. So this graph is for temperature t greater than 0 Kelvin. Okay. Now along the y-axis we plot probability of occupancy, that is f of epsilon. Okay. Suppose this point indicates probability of occupancy is 1. So this point indicates probability of occupancy is half. Okay. So at temperature t greater than 0 Kelvin, Fermi energy is the energy at which probability of occupancy is half. Okay. Now we derive the expression for Fermi energy at absolute 0 temperature. Okay. Now we derive the expression of Fermi energy at absolute zero temperature. Let epsilon F0 denotes the Fermi energy at absolute zero temperature. Now the total number of free electron is n equals to integration 0 to infinity dn. Okay, this is equals to integration 0 to infinity f of epsilon g epsilon d epsilon. Okay, now at T equals to 0 Kelvin, f of epsilon is 1 when 0 less than epsilon f0, and this is 0 when epsilon f0 less than infinity. Okay, so this equation can be written as n equals to 0 to infinity f of epsilon g epsilon d epsilon plus integration 0 to epsilon f0, this plus integration epsilon f0 to infinity f of epsilon g epsilon d epsilon. Okay, so this equation can be written as this. Now if we put the value of f of epsilon in this limit, we get this is equals to integration 0 to epsilon f0, this is 1 into g epsilon d epsilon plus integration epsilon f0 to infinity, and this is 0 into g epsilon d epsilon. Okay, so this is integration 0 to epsilon f0 g epsilon d epsilon. Okay, now if we put the value of g epsilon d epsilon for electron gas, then we will get n equals to 4 pi v into 2m by h square to the power 3 by 2 into integration 0 to epsilon f0 epsilon to the power half d epsilon. Okay, so this is equals to 4 pi v into 2m by h square to the power 3 by 2 into epsilon f0 to the power 3 by 2 by 3 by 2. Okay, so this is equals to 8 pi v by 3 into 2m epsilon f0 by h square to the power 3 by 2, or 3n by 8 pi v equals to 2m epsilon f0 by h square to the power 3 by 2, or 2m epsilon f0 by h square equals to 3 into n by v by 8 pi to the power 2 by 3. Hence epsilon f0 equals to h square by 2m into 3, and capital N by v equals to small n. So this is equals to 3 into small n by 8 pi to the power 2 by 3. So epsilon f0 is this, where small n is the density of electrons, that is number of electrons per unit volume. Okay, and this is the expression of Fermi energy at absolute zero temperature. Okay, now the value of epsilon f0 are of the order of, that is epsilon f0 are of the order of electron volt. Suppose for example for copper its value is approximately 7 electron volt, and for suppose for sodium it is approximately 3.1 electron volt, and so on. Okay, now at last we want to draw energy versus distribution of particle graph. Okay, if we plot energy epsilon along x-axis and number of particles, that is n epsilon, along y-axis, then at absolute zero temperature we will get this type of graph. So this is epsilon F0, that is Fermi energy at absolute zero temperature. So this graph is for temperature T equals to 0 Kelvin. Now for temperature T greater than 0 Kelvin, we will get this type of graph. Okay. So this graph is for temperature T greater than 0 Kelvin. Okay. So these are the important characteristic features of epsilon versus n epsilon graph. Okay. Thank you for watching this video.